Other one, June 25th. Doesn't have much energy today. Binary search tree to greater sum tree. Given the root of a binary search tree, convert it to a greater tree such that every key of the original binary search tree is changed to the original key plus the sum of all keys greater than the original key. All values are unique. Less than on the left, more than on the right. So original is this. So what we want is for each key, I think it's just for the value, to be the original plus the sum of all the keys greater than the original key. So basically 4 plus everything here. All right, which is 5, 6, 7, 8. It's 20, 26. Therefore, it's a 30. So basically, each one you need to add everybody on the right. Oh, but for here, it's also different because this needs to add basically everything here plus this. Okay, so we start from something. We start from the root. We'll go right first, and eventually we'll get the sum of the right. And then when we go left, we'll pass the value of whatever we have to here. And this one will add whatever gets passed, and then add whatever is here. Okay? And we'll return. Return what? I need to return everything. Return all the sum. Yeah, so go left and right and we'll return all the sum. Okay, we'll return all the sum. Alright, so basically we need is a private int BFS retreat. Int BFS tree node, and we also need int previous sum. Okay. All right. So what we need is and we need to return. I'll just change value. Yeah, I'll just change in place. I'm not gonna create a new one. Alright, so basically what we're saying is we have the pre-sum and we have the current, so we can say write our sum shall equal to BFS node dot write. And if you go to the right, you don't have a pre-sum, right? You go to the right, you don't have the pre-sum because nothing is bigger than you. Whatever is going in there. No, you actually do passing down. You do passing down. Like on this side, you do passing down, right? Because you want to do this, you need a previous, and that's going to the right. But how do I know whether I need to pass down? Well, if we have a previous, right? So I should do a pre-sum here. Well, of course, we should first do if node is equal to no, we shall just return 0, right? Nothing. So we'll do the right sum, we'll do a left sum. So what do I pass to the left sum? So for the left sum, we should pass myself, right? We should pass myself. Pass myself after it has been concluded. Right, pass myself after I've been concluded. So we should say int current shall equal to pre-sum. I always do that. And current plus equal to rsum. Once we do that, we're gonna pass the current to this. And once we're done, we say node dot value or equal to current, and we'll return rsum plus left sum. Well, we actually probably can do it here this way. Oh. We probably can do it. So shall equal to plus equal to, right? Plus equal to pre-sum plus BFS, yeah. So I don't need this. We do need rsum. Oh, so we do need rsum. Redo. We will do rsum. Okay, so we don't need this, right? And with rsum plus this is gonna be node dot value. Right, so we first find the sum on the right, right? We find the sum on the right, and once we find the sum on the right, we can update the current. The current is just the pre plus the sum on the right, and then we do the sum on the left, right? So we will do BFS root. Initially it'll be 0. So we do all that, and then we'll return root. Okay, let's give this a shot. Oh. And see if it works. It's not working. Interesting. Why is it not working? Why is this not working? Output, I'm not changing anything. Oh, I am changing something. Oof, that was rough. It didn't change much. Huh, interesting. That is very interesting. All right, let's see. Is this is right? Node dot val plus equal to this. I think the only thing I change is this, the 1 becomes 5. And then 6 and 11. All right, this is not right. This is so wrong. All right, let's go through this whole thing. We got a 4, that's the start, right? We have the root, and it's not equal to no. So I do BFS node R right. So we do this, and then we do this, and then we do this, and then we do it's right, right? So return 0. So R0 is 0. So this node val is 8. 8 doesn't change, and we'll return this awesome is 0, and then we go to the left, which is also 0. So this one return here is 8. Right? And six, 5, 5, 6, 11. Now this one have 11. That's funny. 11. What in the world is 11? So we here, right? So right, this one shall return 8. Prism is 0. Plus equal to. This one should already give me 15. And it's left doesn't, so should return 15. Wait, what? Man, that doesn't make any sense. Does it? Right, that does it. Alright, I need to print some stuff. I need to print some stuff. System.out.println string.format. So first is going to be node.val, okay, and rsum and presum. This is getting really out of hand. 800, that's the first one. And then we have 700. How is this 700? How is rsum equal to 0? Huh? What in the world? Oh. Oh, wow. Have mercy on me. Have mercy on me. I forgot to add node.val. Okay, so now we are kind of wrong. We got 8. We got 15. Okay. But we don't get 21. We get 29. So why do we get 29? Because on this one, I shall only return the original. Damn. Yeah, I think this should only add the original instead of putting everything in. Okay. So node.val is already adding the presum and adding the rsum. So when you return, I don't need to add. So we can do some. We can do this minus presum, right? Minus presum. So we just do rsum plus this. Okay, let's see. Now that is correct. We have 1038. Right, during BFS, we hit write subtree first and get a sum of all its nodes, right? Then we update the current node's value. Pay attention that the current node needs also to inherit value from its parent if its if it is the left tree, if it's the left subtree or left child. And finally, we return the total sum, right? The total sum of the current subtree. All right, let's see. All right, looks about right. It's correct. Note sum, using a list to emulate. Now this is just a sum, right? And now we did a no sum. Come in. If this, I don't return anything. Otherwise, we go to the right, which I think it adds, put it in the no sum, and then we'll plus the root value. And then root of value, you go to this, we update its value. Then we go to the left. So it's similar. I use a return value. They use this to keep track. So node sum will be, well, that's different. I have also a pre-sum. They don't even do a pre-sum. Oh no, nobody's gonna do Morris traversal. Okay, I still try to understand. So I go to the right, go right, and I add its value, okay? And I add the root value. Then I go to the left. And each time I add its value. So basically we collect all the sum on the right first. Right, we collect all the sum on the right, and then when we reach the left, we'll put in whatever is on the right. Huh, that's actually pretty smart. Yeah. Yeah, all the values on the right, all the value, we keep track of all the values on the right. And then when I go to the left, we'll add all the values on the right. All the values on the right. We'll keep all the values on the right relative to the current. And then when we go to the left, we'll add that as well. And we'll add it to it. Then we go here, then we'll go, and then this will add everything here. Oh, this is good. This is very good. Mine is not that bad. I have a presum, which means you have to pass, when you go to the left, you have to pass a presum, which is everything here, right? And then when you go to the right, you just use the previous presum. You keep going. And if you go to the left, you use the current node value, because when you go to the left, current node value collects everybody. Okay. But it's good. We should do this again. So this is the official solution, where we keep track of the sum, right? The sum of all the right nodes at the moment. And we can say int right r sum to 0. Okay, then we don't need to do any of this, right? We also don't need to return anything, so this is going to become a void, right? So we just return, right? Otherwise, we will BFS, right? Node dot right. We go to the right first, and then we will say this shall equal to, shall plus equal to, because we say that our sum is all the sum on the right side compared to the current node, which includes in its parent and everybody on the right. Right, this is everybody on the right. So we do that, and then so our sum is the r sum plus equal to node dot val. Node dot val will equal to this dot r sum, and then BFS node dot left. Right, the right sum, I'll keep track of all the right sum, and then when I hit a current, I have everybody on the right, so I add myself to it, then I can put myself on, and then we go to the left, the current node's left, and then the right sum just keep at it. So we just need to do this, and we return. Okay, let's see. This is another solution. Yeah. Okay, so that's that. Yeah, why don't we do this one more time? I think we just need to use, yeah, this is the one where we need to use two, right? Two monotonic arrays to keep track of the min and max, right? To keep track of min and max. So one is going to be the monotonic decreasing array, so that will keep track of the max at the moment. And the monotonic increasing array, that will keep track of the max, the min at the moment. Every time we do it, we'll check both. Right, we'll check both. If it's within the range, all good. If not, then we need to start removing. So we have a left and a right. So on the left hand side, I need to remove. How do you remove? So basically you need to remove until the minimum gets out, right? So what you can do is keep going until you hit yeah, you can say we have a large and then we have a small, right? And then it doesn't work. Then we need to start shrinking. So we need to shrink. Until, how do you shrink? Because if I have something big, I have something small, right? And then everybody needs to be removed until one of them can be removed, right? Until one of them can be removed. So we'll remove one side. We'll go until or do I? Okay, alright, this is a part I don't understand. Let me see one more time. 2 decks. How do you remove? I know there's 2 parts. How do you remove? Yes. Out of the current window. If max deck, which is the max, is equal to, we pop. Otherwise, otherwise we move the left. We move the left forward. Okay, we move the left forward. Which means if both are not, we'll move the left forward. Until we find where this is equal to. So equal to one of them. Right, if it's equal to one of them, then, oh, this is great. This is some great piece of work right here. So the condition is to make sure, so what we want to make sure is the current subarray, the max minus minimum is smaller or equal to the limit, right? So we use that as a loop variant, and as we go, because we need to shrink them, but we don't know which one to shrink first. That's the thing, we don't know which one to shrink first. So we have a pointer on the left to go one by one. For each one we compare, we check with the 2, right? If the first time it equals one of them, then we'll pop that side, right? And then I'll check again, right? And then if it satisfies, then we're good. If it doesn't satisfy, we'll keep popping. That is very interesting. Okay, so I took a look at this, so I cannot do it today. I have to wait until tomorrow to kind of let myself forget about it again. But one thing for sure, we can do this. Yeah, we're not going to use the previous one. All right, anyway, I'll end it today, and I'll see you